Hi all. So today we are going to look at we are going to continue with our module number 3, and today we're going to look at first one is polarization, and then we are going to look at the power of EM wave, and then we are going to look at the reflection and transmission of EM wave in a boundary. When the wave is in normal incidence. Okay. So let's start with polarization. Now you define polarization as the locus of the tip of electric field at a given point as a function of time. Okay, so we will elaborate this. So what it is meant is something like this. We know that our electromagnetic wave will have a direction of propagation, okay, and then there will be electric and magnetic field in perpendicular to the direction of propagation. So I'm not drawing the magnetic field, I'm drawing only the electric field. So this electric field, we already saw that it will be some kind of a sinusoidal variation, something like this. And we also saw that there will be an orientation of electric field, something like this. Now whatever I have drawn, the electric field here is currently oriented in only one direction. So if the wave propagation is in z direction, then I can say my electric field might be in x direction. Okay. Now if you look at this electric field, you see how the tip of the electric field varies. So this is actually the tip of electric field. So the definition of polarization is how the tip of electric field vary, or locus of the tip of electric field at any given point. So if you are looking this wave from here, okay, then when you see the wave coming towards you, you see that the electric field orientation is in a straight line. So you should imagine that you are looking from this direction, and you see that the electric field orientation will be something like this. So this is, let's say, z and x. So your electric field will be something like this. Okay. It will be moving up and down when you look it from here. Okay. Now this is called as polarization. So you can map the three-dimensional wave electric field orientation to a two-dimensional axis, and the locus of the tip of the electric field gives you the polarization. Now if you look at this, it is in a straight line. The tip varies in a straight line. This is called as linear polarization. Okay. So we told that the electric field can orient in any direction. It can always be perpendicular to the direction of propagation. Now I can have the electric field something like this. Let's say and the electric field orients like this. Okay, and the direction now is, this is Z, wave is still traveling in Z direction, and this direction is Y. Okay, so now if you look at from here, okay, now if you look at from here, then you see that the variation is still linear, but now it is in Y direction. Okay, now the axes are X and Y. So let's say I have my Y something like this. So now my electric field will vary like this. This is Y, this is Z. There is no variation in X direction. This is X, there is no variation. But still it is linear, because the variation is still linear, because of which it is a linearly polarized light. Now there is another option in which, see, in this scenario we said that there is only either electric field has either X variation or Y variation. Now the wave can travel at any direction in free space. So what about there is an arbitrary direction? For example, let's say this is the direction of propagation. Now let's say the wave is traveling like this. Okay, where this is X, okay, and this is Y. Okay, and the wave is having some component along X and Y. Okay, that means if I represent my electric field E something like this, so this is my axis and the electric field E is at some arbitrary direction which I can resolve for X and Y. Okay, so if I can resolve, so this electric field now has component along X and there's a component along Y. Now let's assume that it is not constant, means it keeps on rotating. I try to draw this, I don't know whether I will be successful in drawing this, let me try. So this wave now goes something like this. Okay, so at t equal to 0, so this is at t equal to 0, Now at some t equal to t1, the wave has rotated. The electric field of the wave has rotated. So in that case, my orientation will be something like this. Let me draw with a lighter color so that it will be visible. Okay, so the wave has now rotated. Now at t equal to t2, the wave might have rotated again. So something like this. I think I won't be able to draw that. So basically, the wave will be rotating like this. The direction of rotation is still said, but the electric field keeps on rotating. So now if you look from here, you see that your locus of the tip actually follows a circle. Okay, and this is called as circular polarization. Okay, so here what I meant is, so tip was here now initially. If you take only this tip, then the tip came here, and then tip comes here, comes here, comes here, comes here, comes here, and it goes on back. Okay, so when you look at from here, you see only a circle. If you look at this tip only, you see a circle. So the tip follows a circle. So the electric field need not be always in the same direction. It can rotate along the axis of direction of propagation. So this is the direction of propagation. The electric field rotates along this axis. Now when the electric field rotates, it is still perpendicular to a direction of propagation, and the magnetic field also be perpendicular to a direction of propagation, and electric field and magnetic field will be perpendicular. So when electric field rotates, the magnetic field also rotates. And when you trace the path of a tip of the electric field, the orientation, you can see that it follows a circle. This is called as circular polarization. Similarly, in a similar way, there is something called as elliptical polarization. We'll see the condition. Circular polarization is actually a subset of elliptical polarization. We'll see how that happens. Understood the concept. So here the electric field is getting, you are looking at any tip of the electric field orientation, and you are checking how it orients at any time. Okay, so there can be two polarization. One is linear, one is circular, and there is elliptical. Okay, now let's understand the mathematical part of this. We already told that our electric field need not be always in x or y. Let's say it can arbitrarily in x and y. So electric field need not be always in x or y or z. Can always go in z also. So it can have any arbitrary direction. Now if it is in any arbitrary direction, you can resolve, or you can create components of this electric field along x and y direction. So if any arbitrary direction, implies you can resolve or create components of electric field along x and along y. So what do you mean by that? This you might have studied already in your lower classes. Let's say your electric field is something like this. Okay, the orientation, that means the tip of the electric field is something like this. This is along x, this is along y. Now, since it's a vector, you can resolve it into two components. One is along x direction, which I call as Ex, and one is along the y direction, which I call as Ey. Okay, and there is some angle which it creates with x. Okay, so I can always resolve electric field into two components along x and y. Okay, so let's say my Ex is equal to some constant Eox cos of omega t minus beta z plus phi x, and Ey is equal to Eox cos of omega t minus beta z plus phi y, where phi x is actually the angle E makes with x and phi y is the angle the E makes with y. Okay, we already know that the electric field follows this equation, where this cos omega t minus beta z plus the phase it makes with x or y. Okay, now for linear polarization, the condition is one. Sorry, I made a mistake here. This is Ey, E0y. 1. E0x should be equal to E0y. The magnitude of the electric field components along x and y should be same. Okay. And also the second condition is the phase difference, that is phi x minus phi y or phi y minus phi x, should be a multiple of pi, where n is 0, 1, 2, etc. Okay. So if, for example, is let's say phi x is equal to 0 and phi y is equal to pi. Okay, so in this case, then Ex and Ey will follow linear polarization. Okay. Similarly, for circular polarization, then the first condition is the magnitude Eox should be is equal to Eoy, and the second condition is bit different from that of the linear. This is del phi, or the difference between x and y phase difference, should be an odd multiple of pi by 2, where n is 0, 1, 2, etc. So this means this should be an odd multiple of pi by 2. Okay. For example, phi x is equal to 0 phi y is equal to pi by 2. So in this case, Ex is equal to Eox cos of omega t minus beta z. Ey is equal to Eoy cos of omega t minus beta z plus pi by 2. This is equal to Eoy sin of omega t minus beta z. Now if you square Ex square plus Ey square, this is equal to Eox square cos square omega t minus beta z plus Eoy square sin square omega t minus beta z. So now we already know the condition Eox should be equal to Eoy. So I can write Ex square plus Ey square is equal to Eox square multiplied by cos square omega t minus beta z plus sin square omega t minus beta z. And we know that this quantity is equal to 1. So this is equal to Eox square. So basically Ex square plus Ey square is equal to Eoy square, or this is similar to the equation x square plus y square is equal to r square, which is the equation of a circle with center 0, 0 and radius Erx. So the locus of the tip of the electric field will follow circular polarization if the magnitude of the components of the electric field along x and y are same, and the phase difference between the components is an odd multiple of pi by 2. Okay. Now these two are special cases of something called as elliptical polarization. In which the condition is Eox need not be equal to Eoy, and the phase difference delta phi should be phi x minus phi y is equal to plus or minus 2n plus 1 into pi by 2 comma n equal to 0, 1, 2. Okay. So the equation of the ellipse in this case, when taking an example, let's say phi x is equal to 0 and phi y is equal to pi by 2, and we know that Eox not equal to Eoy, okay, is same as this one, okay, and this you can write as Ex square by Eox square plus Ey square by Eoy square is equal to 1, which is actually an equation of ellipse. Okay, so that's what a polarization is. Now polarization is a very important concept in electromagnetism, where it will be used heavily in antenna and wave propagation, and even in microwave and radar engineering. So although it looks very simple, you should understand what a polarized light means, which is evident from the diagram here, which I'll try to elaborate using a video maybe in the next lecture. And using the polarization, you can filter out many parts of the light. There are, for example, your sunglasses. It actually filters out a particular polarized light so that the intensity of light reaching your eyes is less. The 3D glasses that you wear in cinema theater, it's actually a polarized glass which rotates the light in two different directions because of the two glasses in the two eyes. So all these are applications of polarization. So this is regarding polarization. Next, we are going to look at power and Poynting vector. Okay, now we talked a lot of things about electromagnetic wave, that there's an electric field, there's a magnetic field, there's a direction of propagation, there are a lot of parameters associated with the wave. Now since there is an electric and magnetic field, now it also involves some amount of energy. You know, we have derived an expression for energy stored in electric field. Similarly, there is an expression for energy stored in magnetic field. So if a wave is propagating with an electric field and magnetic field, how much amount of power is associated with that wave? And that is what we are going to look at in the next section. So what we are going to see is something like this. Let's say you consider a small volume. Okay. Now the volume is very small, so that the electromagnetic wave just has enough energy to just pass through it. So the wave will propagate through this volume and comes out. Now this wave have the corresponding electric field and the corresponding magnetic field. The wave coming out will also have the electric field and the corresponding magnetic field, and both are perpendicular to the direction of propagation. Now when the wave goes in, before the wave goes in, let's assume that this volume doesn't have any kind of energy, doesn't have a variation in energy. It has a constant energy. It might have an electric field inside it, it might have a magnetic field inside it, but whatever it is there, it is having a constant energy. Now when the wave gets incident on this volume and comes out, there will be some change in this energy in the volume. That change in the energy or the power in that volume is the power due to the wave, because according to superposition principle, you can't create energy or destroy energy. So whatever extra energy is coming in that volume is because of the energy incident by the wave. And rate of change of energy is basically the power. So we are going to find out what is the power associated with a wave by looking at the change in energy or power in this volume when the wave propagates through it. Okay. So let's start with our Maxwell's equation. Del cross E is equal to minus mu dou H by dou T. Here be careful, we are not using any phasor notations. We are just using the actual electric and magnetic field notations. And also del cross H is equal to sigma E plus epsilon dou E by dou T. Okay. Let's say this is equation number 1, this is equation number 2. Now let's take dot product on both sides of equation number 2. So I have E So we are taking dot product with the electric field. E dot del cross H is equal to E dot sigma E plus epsilon dou E by dou T. Now I can take this E inside in the right hand side. So this is sigma E dot E plus E dot epsilon dou E by dou T. Now E dot E is, we have already seen, this is the magnitude of E square. Okay, so I can write this as E dot del cross H is equal to sigma determinant or magnitude of E square plus, you can take epsilon out because it's a constant, into E dot dou E by dou T. Let's say this is equation number 3. Now let's look at the LHS of 3. We use an identity which is as follows. Del dot A cross B is actually B dot del cross A minus A dot del cross B. This is a well-known identity. Let's take the negative term from RHS to LHS. So I can write B dot del cross A is equal to, so what I did is I'm going to take this to this side, is equal to del dot A cross B plus A dot del cross B. Okay. Now let's say our A is equal to H and B is equal to E. So implies I can write E dot del cross H is equal to del dot H cross E plus H dot del cross E. Okay. So let's say this is equation number 4. Now let's substitute equation number 4 in the left hand side of equation number 3, because you see that the left hand side of this equation number 4 and equation number 3 are equal. So I can just substitute whatever is in the right hand side of equation number 4 into the left hand side of equation number 3. So I can substitute RHS or substitute RHS of 4 in LHS of 3. So I can write as del dot H cross E plus H dot del cross E is equal to sigma magnitude of E square plus epsilon E dot dou E by dou T. Okay. Now we want to find what this expression is. E is a function of time also, so you cannot directly take E inside. Instead, we are going to look at what happens if you take E inside. Okay, so what is dou by dou t of E dot E? This is equal to, since E is a function of time, you cannot just say it is magnitude of E square, okay, because you need to differentiate with respect to dot product. So I can write this as, using the chain rule of differentiation, E dot dou E by dou t plus E dot dou E by dou t. This is equal to 2 times E dot dou E by dou t. Okay, and this expression is dou by dou t of magnitude of E square is equal to 2 into E dot dou E by dou t, implies E dot dou E by dou t is equal to 1 by 2 dou by dou t of magnitude of E square. So this you can substitute. So this you substitute it in here. Okay, so let's name that equation number 5. So I can write, substituting equation number 5 in RHS of, let's say this is equation number 4a. 4a, you will get del dot H cross E plus H dot del cross E is equal to sigma magnitude of E square plus 1 by 2, or I can write, okay, 1 by 2 epsilon dou by dou t of magnitude of E square. Okay, now let's look at this part, H dot del cross E. So H dot del cross E is equal to, we know that del cross E is minus mu dou H by dou t. So this is H dot minus mu dou H by dou t. This is equal to minus mu H dot dou H by dou t, and using the similar way here that we have proved here, you can write this as minus mu into 1 by 2 dou by dou t of magnitude of H square. Okay, and you can substitute this in here. So I can write, so let's say this is equation number 6, this is equation number 7. So you say 7 in RHS of 6 implies del dot H cross E minus mu by 2 dou of mod H square by dou t is equal to sigma mod E square plus 1 by 2 epsilon dou E square by dou t. Okay, now I am taking the second term to the right hand side. Okay, So I can write del dot H cross E is equal to sigma magnitude of E square plus 1 by 2 epsilon dou mod of E square by dou t plus mu by 2 dou magnitude of H square by dou t. Okay. Now let's rearrange this term. We know that A cross B is equal to minus B cross A. So I can write this as minus del dot, let me just put minus del dot E cross H is equal to sigma magnitude of E square plus 1 by 2 epsilon dou magnitude of E square by dou t plus mu by 2 dou magnitude of E square by dou t. And let's take the negative sign to the other side. So I will get del dot E cross H is equal to minus, I can write as sigma mod E square minus, just combine these two as 1 by 2 epsilon dou E square by dou t plus mu by 2 dou H square by dou t. Now we told that this is for a wave across a volume, okay, and we can take the volume integral of this to find out how much is the change. So taking volume integral on both sides, we get integral, this is a volume, this is a triple integral del dot E cross H dV is equal to minus 1 by 2 or minus dou by dou t, the volume integral 1 by 2 epsilon, let me put as epsilon by 2 mod E square plus mu by 2 mod H square minus volume integral sigma E square dV. Okay, and you can write this using divergence theorem. So applying divergence theorem to LHS, you get surface integral E cross H ds is equal to minus dou by dou t volume integral 1 by 2 epsilon mod E square plus 1 by 2 mu mod H square dV minus integral volume integral sigma mod E square dV. And this is the final expression. If you look at the right hand side of the expression, you see this is actually the energy in an electric field. And this is actually the energy in a magnetic field. And this is actually a rate of change of energy because there is a dou by dou t, and there is a decrease in energy because there is a minus sign. So this is actually a rate of decrease in energy stored in electric and magnetic fields. Okay, how? Because 1 by 2 epsilon mod E square is energy in an electric field, 1 by 2 mu mod H square is energy in a magnetic field. Now when I do dou by dou t, you are actually finding out the rate of change of energy. Now since there is a minus sign also, we say that the decrease in rate of or rate of decrease in energy stored in electric and magnetic field per unit volume. Okay, and this one is actually ohmic power dissipated, because sigma is E is as per Ohm's law, J is equal to sigma E square is the power dissipation, basically because of some resistance. Okay, so when you combine all this, you can say this part is the total power leaving the volume. So what does it mean? We told that there is a volume, and we told that there is an electromagnetic wave propagating through the volume which has an electric and magnetic field. Something like this. Now the total power which is going or total power which is leaving the volume is basically equal to the rate of decrease in energy stored in electric and magnetic field in this volume and the ohmic power loss. So that is the, so whatever energy change has happened in this volume, that is because of the electromagnetic wave propagated. And the total power leaving the volume is given by integral E cross H ds. And you say this expression, let us say P is equal to E cross H is called as the Poynting vector. Since it is a cross product, the direction is perpendicular to both E and H, which is actually is the direction of propagation. So the power is transmitted not along electric field direction or not along magnetic field direction. The power is transmitted along the direction in which the electromagnetic wave is propagating. This is called as Poynting vector, and we state it using a theorem called as Poynting's theorem. Okay, so the Poynting theorem states that the net power flowing out of a given volume V is equal to the time rate of decrease in the energy stored within the volume V minus the ohmic loss. So the net power flowing out, which is this expression on the left hand side, is the rate of change of decrease or rate of decrease in energy in that volume, which is the first expression on the right hand side, minus the ohmic loss. That is what states in Poynting theorem. And P is equal to E cross H is the Poynting vector, and it represents the direction of flow of power. So this actually is the direction of flow of power. Okay, this is called as the Poynting vector. Now we define something called as time average power. Okay, because the Poynting vector here, so E is a function of the position and time, H is a function of position and time, so the P is also a function of position and time. So I can write P, or let me choose a different color. The Poynting vector P is actually a function of the position and time. So it need not be said, it can be any arbitrary position. So we define something called as P average, as which is only a function of position, as the time average of the Poynting vector. Okay. This is called as time average of Poynting vector, where T is the period of the wave. So we take one complete period, we average the power of the wave for that period, and we will find that at a particular position what is the power. So at z equal to 0, you can say that if you look at the wave for, let's say, time period of 10 seconds, what is the average power at that incident on that position? That is the time average Poynting vector. And this is actually, you can prove this also. The time average Poynting vector is equal to 1 by 2 into real part of the phasor notation or the point form of Ex cross Hs conjugate. Okay, this is an important expression. Okay, here note that this is actually the phasor. Okay. Now the total time average power crossing a given surface S is P average. Note that this is not a vector, is equal to, across the surface you average P average of Z for the surface. Okay, this is a total time average power crossing a given surface. Don't confuse this with this P average of Z. So I'll just write as PAVG. just to make sure that they are totally different. Okay, and this is if the wave passes through a surface, what is the total power passing through that surface, or a time average total power. If you consider the surface, if you look for some duration of time, if you let the surface have some distance where the wave is passing, what's the total power passing through the surface? That is given by this expression. And note that all these power values are totally different. So it is averages at different points in time and space. Okay, and this is a scalar. Make sure that this is a scalar. All other powers are vectors, and all other powers have the direction equivalent to the direction of propagation. Okay, so you have understood this concepts of polarization and time average power. We will be looking at reflection and transmission in the next lecture, because I don't think we'll have enough time to